Welcome back to the Dr. Stats-A-Lot channel series on probability theory. I'm Mark Ledbetter, and in this video we cover Part 2 of Chapter 5, Section 1, which is Functions of One Random Variable. This is Video B of Part 2, and it is the final video covering the transformation of discrete random variables. So let's get started. In this lesson, we'll complete examples of transformations using the inverse substitution method along with the proof method. We'll also use a visualization of the transformation in order to understand its effects. Finally, we'll review what we've learned. We start with the negative binomial distribution for r equals 3 successes with p equals 0.8 as the probability of success on each independent trial. We wish to apply a linear transformation to x, namely 1/3 x minus 1. Here's the PMF for a negative binomial random variable with the values for r, p, and q substituted into the formula. Our space for x is 3, 4, 5 up to infinity. We need to solve the transformation for x. We add 1 to both sides, then we multiply both sides by 3 to obtain x equals 3 times the sum of y plus 1. We start with the probability of random variable x equals to the value lowercase x, and substitute our solved expression for lowercase x. Every lowercase x in the PMF is replaced with the expression involving y. Next, we need to transform x to y to find the space of random variable y. A table makes this easy. You can probably see the pattern of random variable y. It starts at 0 and increases by 1/3. Next, we simplify the PMF to obtain the easiest expression for the PMF of random variable y and include the space of y. It's now time to graph the transformation so we can visualize its effect. The top Excel graph contains the original distribution of random variable x from 3 to 7. Recall that the space of x extends to infinity, but this shows 5 points and gives an adequate idea of what's occurring. The bottom Excel graph contains the transformed distribution of random variable y. We see the mapping of x equals 3 to y equals 0, x equals 4 to y equals 1/3, x equals 5 to y equals 2/3, x equals 6 to y equals 1, and so forth. Our linear transformation is 1/3 x minus 1. The scale factor, or parameter, is 1/3, which compresses the spread of the distribution. And the location parameter is -1, which shifts the result of 1/3 x 1 unit to the left. In example 4, we explore the effects of a quadratic transformation on this discrete distribution where x takes the values from 0 to 3. The transformation is defined in such a way that we have a linear transformation that is squared. There are other ways to define a quadratic transformation, such as a times the quantity x minus b squared, but our expression is one that does not have many published examples. We will solve for lowercase x in the transformation. When we take the square root of something, technically the answer is plus or minus of the square root. However, in this case, all the values of x are non-negative, so we will only use the positive values of the square root. We replace lowercase x with the equivalent expression containing y. Now we replace all lowercase x's in the PMF of random variable x with the quantity 1/2 times 1 plus square root of y. Next, we use a table to find the allowable values of y. Now we simplify the PMF and add the space of random variable y. Unfortunately, when 2 or more values of x result in the same value of y, we have a 2-to-1 result. Anytime this occurs, the square function is not a 1-to-1 function, it is a 2-to-1 function. In the table, we see that both x equals 0 and x equals 1 are transformed to y equals 1. Unfortunately, when 2 values of x result in the same value of the transformed random variable y, the inverse substitution method will not work. In the table, we have transformed each individual value of x. Notice that both x equals 0 and x equals 1 transform to y equals 1. We will have to add those probabilities. Now we have the complete PMF for random variable y. The upper graph shows the PMF of our original random variable x. The lower graph contains the PMF of the transformed random variable y. We see that both x equals 0 and x equals 1 are translated to y equals 1, and we add those probabilities. This results in a different shape for the distribution of random variable y. Notice how the coefficient of x is greater than 1, which expands or spreads out the distribution. The constant inside the square reduces the value by 1, and the square amplifies the effects by spreading the distribution more. In example 5, we use the same distribution for random variable x that we used in example 4. Now, we explore a quadratic transformation that is only slightly different. We're going to replace the minus sign inside the parentheses with a plus sign, and that is all. This quadratic transformation does not have any 2-to-1 relationships, even though we use the same values for x that we used in example 4. In other words, each value of random variable x translates to exactly one value of random variable y. When we solve the transformation for lowercase x, we choose only the positive square root, since all the values of random variable x are non-negative. It is always a good idea to verify that the PMF values for y add up to 1. For finite spaces of x and y, a table is a very easy option to do this. For discrete random variables with infinite supports, you may have to use your knowledge of summations for infinite series that you learned in Calculus 2 or 3. So let's see the effect of this transformation. The upper graph shows the PMF of our original random variable x, and the lower graph has the PMF of the transformed random variable y. Each value of x gets translated to exactly one value of y. In other words, it's a 1-to-1 function. The coefficient of x is a positive 2, which is greater than the absolute value of 1, so it's going to increase the spread of the distribution. And the positive 1 inside the parentheses is the same sign as the coefficient positive 2, so it also increases the spread of the distribution. Finally, the square spreads out the distribution even more because the values inside the square are greater than 1. In example 3, we applied a linear transformation to x, which was y equals 1/3 x minus 1. The coefficient of x acted as a scaling parameter. The 1/3 is less than the absolute value of 1, so it reduced the scale or spread of the distribution. The subtraction of 1 shifted the result to the left by 1 unit. In examples 4 and 5, we used a quadratic transformation that had the form y equals, inside parentheses, a times x plus c, quantity squared. If 2 or more values of x in the support of the original PMF result in the same value of y, the inverse substitution method will not work for all values of y. So it's always a good suggestion to use a table to verify the mapping from x to y is 1-to-1. Notice that for this form of the quadratic equation, if a is greater than the absolute value of 1, it's going to increase the spread. But if a is less than the absolute value of 1, it decreases the spread. If c, the constant, has the same sign as a times x, it increases the spread of y. But if it has the opposite sign of a times x, then it decreases the spread of y. So the effect of the constant c depends on the sign not only of itself, but also the sign of a times x. Well, this concludes our exploration of discrete transformations for one random variable. In the next set of videos, we will delve into the transformations of one continuous random variable. I really hope this video was helpful to you. Please remember to click on the link in the description for the worksheet. Most importantly, please stay safe and take care of yourself, because I hope to see you here next time.